Hi everyone, welcome back. So in this video, we'll showcase how to set up our simulations now, and then if we have time for it, we'll extend it into generating the S parameters. So what we'll do here is we'll comment out the code here at the very bottom. We don't need this anymore, but we can just leave it here in case we want to look at the layout. So leave a little note here that says layout, and then instead we'll add some code to create the simulation. So we'll create a simulation object called simCDC. It will be our device object, but we will pass to it that the simulation geometry should be true, because this is for simulation and not for layouts. Next, we'll create a sim layout object, and we'll initialize it. So it's sim_cdc layout, and this will give us our geometry. And then next, what we want to do is we want to create a geometry object. We'll call it simGeom, and this will be an i3 device sim dot simulation geometry. And this is just so we can take the element we extracted from the layout object and pass it to the device simulation. So this function here takes one argument called layout, and we'll just point it at our layout object. And that'll create a simulation object that IPKISS's built-in numerical interoperability functions can utilize. So finally, we can create our real simulation object called simulation. And this will be the built-in IPKISS function that connects to Lumerical. So it's i3 device sim, and what we want to call is we want to call Lumerical EME simulation. And this function here takes a few things. So first, it can take headless. So we're going to set that to false. We want to see the UI. Next, it takes geometry. And we can point this at our geometry object we just created above. And then finally, it takes something called outputs. And then it also can take setup macros in this exact wording format. So make sure your syntax are correct here when calling these properties. And that is pretty much it that we can add to it. And then finally, once we have our simulation object, we can inspect it. So we can say simulation.inspect if we want to. We can also say we can also use simulation.getResults if we want to. And this can specify something else later. So we'll just leave this as a comment for now, and then we'll update it in a little bit. So this will be enough to create our simulation object, as we did before in our brag example over here. So feel free to review it if you want to go into further details. But what we want to do next is, this time, we want to create a setup macro. And the reasoning for this is because with this device, it's a bit more complex. We want to make sure we capture the coupling. So a bit of the EME in Lumerical's parameters need to be adjusted. We also need to map the ports correctly. So that's where this will go into the setup macros. So the setup macros are a bunch of scripts that initialize when Lumerical EME launches, and we can just put them in here instead. An alternative thing you could do is you could also create a normal macro, and a normal macro can also be executed through this simulation object. So I'll show both here. So first, with the setup macro, what we want to do is we want to do a i3.deviceSim .Lumerical macros. This is a built-in function in IPKISS, lets you run macros that they have already. And the macro that I'm interested in is something called EME setup. So this will help me set up the EME without me having to go into too much LSF scripting on the Lumerical side. So the values I want to change for this EME solver is the group span. And the group span will be an array. And then I also want to edit the cells, which will also be an array. And that would be enough for me. So in the group span, what we want to do is we want to give it the span of our unit cell. So the span will be simcdc.period. So here we're calling this CDC object we created, so specific to this device, whatever its period is, divided by 2. And then we want it to end at simcdc.period divided by 2. So this is just how wide that group span is for each of the table parameters. So if I open numerical here, let me find numerical mode here, just so we can visually see what we're editing. This will be under the EME object. So we'll go into numerical mode. Sorry, kind of slow today. And we'll just create a structure. We'll go to the simulation tab here. And then we'll create a EME solver. So in the object, we have group spans. And this is just how wide each value is. So if we had, let's say, 2 cell groups, which is what we're aiming for, you'll see that there's 2 columns for the group span. And this is what we're editing here. We want each of these to be half of the period because together they make the full unit cell. So that's why each of these values are half the period. Next, we have 2 cells. So we'll just determine them there as cells 1 and 1. And this value corresponds with this value here, cells. And then what we'll want to do next, similar to the Bragg straight wave guide, is we also want to set up the cell groups. And using the cell groups in EME here, over here, the periodicity, we can artificially propagate these unit cells to whatever length we wish them to be. So we want to manually set this up. So ideally, in our case, it looked like a cell group in 1 and 2, and then it has a period of, let's say, I don't know, 300 or 500 or however many. So we can't do that with the EME setup, unfortunately. It's not one of the functions that is provided. However, we can use a custom macro instead. So here we'll add a comma to our first macro. So that's the first macro that will run. Next, we'll create a custom macro. So you can create custom macros using IPKISS, using i3.deviceSim again. And then this time we call the macro function rather than the numerical macros. So these are more generic. And then in it, there is a commands variable, and we pass it a list of commands. So inside here, we can actually do LSF syntax scripts. So what we'll do here is I'll copy over my LSF script from another file that I made up already. And I'll go through them one by one, what we're doing. So in this LSF script, we'll first do selecting the EME object. And then please be sure to include this semicolon, as it is necessary for numerical to process it. Once we have the EME object selected, we can edit it now. So the first thing we do is we set the energy conservation value to conserve energy. So what it looks like here is if we open up numerical, we're going into the EME setup tab, and then we're making this conserve energy right here. Next, what we'll do is we'll make a f string. So an f string allows us to use our variables and turn them into strings. So we want to set the y span. We basically select our CDC object up here, and then we want our y span to be the waveguide width. Make sure we set it to microns in this case. Numerical operates in meters otherwise, so you're going to get something very huge if you forget this conversion value here. And then plus the gap, and then plus the second waveguide's width, and then plus 1 more micron, just so we have enough of a y span, which would be up here in this XY view, so we capture enough of the cladding. Without the cladding captured, you might get some weird boundary conditions, and it's not really an accurate result of your simulation. So next, what we want to do is we'll also set the background material. So we'll use the built-in material here, silicon oxide. And then we'll set up the cell groups we mentioned before. So we want the cell group to be the first cell group, and it ends at the second cell group. And then we'll set the periods to 500. And then finally, we want to adjust the ports. so the ports are only encompassing one of the waveguides. If we don't do this, what will happen is it'll try to draw ports across the whole device, and then you'll capture the transmission on both devices essentially. So what that will look like is if I use a black pen here, by default the ports are drawn like this, and then there's one of each like that for each of the devices, so you get overlap, and it's not very useful to know what the transmission of each one is. So instead we edit them manually so they draw like this, and then we can get the output of each one correctly. So that's what these lines here are. So going through one of them, we're just going to find the Y span like before, and then we stop it off by the gap. And then this is pretty much a custom macro. You can put any kind of macro into this, and it will work without issue. So with that, I believe we can actually run the simulation and see if it set up correctly. So I have an error with a key argument called group span. So I have a little typo here. It's actually group spans. So just something to look out for here. Since it is kind of freehand when you type these, you're not going to be able to get any kind of suggestions from PyCharm. So it's actually group spans. My suggestion is, of course, to try to do this all in numerical first, and then either load in your LSF script or copy over the LSF script's strings like so. And that'll be a better way to, and more robust way to guess and test, I guess. So here are devices being made. I can see that it drew the simulation geometry, which is good. It looked like it also drew our custom ports and our custom sizes to encompass the clouding on the side. So this looks good to me. So just doing a quick check, we have our first Bragg waveguide down here and the second one on top. They're different sizes, which means that they're written correctly by the CDC class. We can see the ports here. So selecting one of the ports, it stops right at the gap, so it doesn't encompass the second waveguide, which is good. So 1, 2, 3, and 4, they all look good. And then we can also check the EME object here. So conserve energy is set up. The group bands are set up to half the period, which is good. And then the periodicity groups are correct. So cell group 1 and cell group 2, and we're doing 500 period. So we can actually even run this simulation right now and do a quick check of the transmission results. So what we're expecting here now is we expect this device to filter out a spectrum, and within that wavelength range, that filtered out signal should appear on the other port. So our transmission port should be a filter signal, and then our drop port should show the other signal. So if we go to our transmission port here, which is 2.1, 2 is the drop port, so that's our filtered out signal. So if we go to 3.1, which is our throughput port, we'll see that here's our signal, and then at some wavelength, we actually filter out a signal, and then that signal can be seen on our drop port here. So if we go to our drop port, which is 2.1, we have no signal, and then within this range, that signal comes in. So this device seems to be within what we're expecting to simulate. And with that, I'll end the video here. And we'll see each other in the next one. Thanks.